Okay, so this is the 16th lecture I've given, and or is going to be. And what I'm going to cover today is a way to approximate this formal, exact way of dealing with the interactions in particle systems. So what we're going to do is I'm going to show you a very quick and dirty trick for dealing with with this problem. I'm going to show you a quantity called the second virial coefficient. I'm going to give you a very quick hand-waving argument. That's the only thing you really need to understand in anything I'm going to lecture today. Everything else can just go over your head, and if you ever one day need it, then good luck with that. And so this is going to be the most important thing I want to give you is the physics of this. And then I'm going to show you a little bit of a sketch of how one formally deals with this to simplify the work of doing the formal expansion. And the method for, as I said last time, the method of dealing with these closure problems, they're endemic in all interacting many body systems, whether it be in physics, fluid mechanics, anything else. The way you deal with that is by a certain kind of diagrammatic perturbation theory. And the thing that people care about is ways to make that calculation as easy as possible. So I'm going to show you a huge simplification. It still makes the problem incredibly difficult, but it's a result that is derived from graph theory and topology. I'm not going to derive it for you. It's in the note if you want to. I can give a separate discussion session lecture later and show you how you can derive it in detail. I will just sort of skip through it and just show you some of the high points, and if you want, you can read it. All right, so here's the problem. We've got a bunch of particles bouncing around in a box. The particles are interacting with this potential, which I've drawn over here. And what people do is they, we don't have any fundamental understanding of these potentials, but one can write them down under certain circumstances, for example, for van der Waals forces and so on. So there's a lot of empirical formulae that are used, which turn out to be very useful. So one that is particularly useful is this one called the Leonard-Jones 612 potential. And that's the one shown here. So you basically say a hardcore repulsion at small distances goes like 1 over r to the 12th. And the long-range attraction goes like 1 over r to the 6. And in the notes, I've got a simple derivation for the 1 over r to the 6 in terms of dipole moments and van der Waals forces. But and you've probably done that in quantum mechanics, so I'm not going to repeat it. So we're just going to ask what happens then when we're trying to compute the second virial, trying to compute the 2-point correlation function. So our goal in this section is a quick and dirty way to compute G of R. So that's what we're going to do. And our basic idea is the following. So you can see that this potential has a length scale associated with it. It has this R star, which is the mean separation between particles. And if the particles are very far apart, then essentially the potential goes to 0. So basically, the potential is, roughly speaking, 0 everywhere except near R is of order this mean separation, which I called R star. So then what we're going to say then, so let's suppose then that we're at low density. So this won't work at high density, but at very low density, what's going to happen is that the integral, and when I say the integral, I mean this integral here, this integral, the numerator of the 2-point correlation function. that integral is going to be dominated by configurations where most of the particles are very far from particles 1 and 2, and they're also far from each other. So basically, if all the particles are far away from each other, then there's going to be no effect of the interactions. So what that means is that if we're going to have interactions, the only terms that are going to matter, you're going to have particles 1 and 2 to be close, i.e., roughly speaking, R is of order R star. And then also particles 1 and 2 are going to be far from the other particles. So those are going to be this sort of configuration will dominate the integral. So here you can think of it in the following way. So I've got particle here, particle 1 is over here, here's particle 2, so they're very close together, so they will give you some contribution, and then all the other particles are far away from each other, so all the other particles are far away, so I only need to consider that. And so therefore, if that's the case, then if I look at what my if I look at that numerator, so what do I have to consider? The numerator is the integral d3r1, d3r2, d3r3, all the way up to d3rn. So that's the numerator in here. Then I've got to have e to the minus beta over 2, and the sum over I not equal to j of u of rij, like that. Then I have my delta function, delta of r minus r1 minus r2. So that's the numerator. And so what we're going to say is, well, just particles 1 and 2 are nearby. So then I can write this as the integral d3r1, d3r2, delta of r minus r1 minus r2. And then the only term in the sum, in the potential, is the term between particles 1 and 2. So I have that. Well, there's two. Well, yeah. Why? Where did my 2 go? I don't know about that. I'm going to take this 2 out. I don't think it should be there. So it's just e to the minus u of r12 over kt, and then I have all the other terms, and the terms for the other integrals, d3 r3 up to d3 Rn, those don't have any Boltzmann factors at all, because when they're far away from particles 3 and 4, then when they're far away, and that means that U is equal to 0. And so I only get the U is equal to 0, so the Boltzmann factor becomes 1. So the Boltzmann factor is then just 1 for those things, and so I don't need it over there. And so then I can write this as equal to d3 R1, d3 R2, delta of R minus R1 minus R2, e to the minus U of R over KT, and then the other particles just give me a factor of the volume raised to the power n minus 2. Because I just have n minus 2 integrals, and there's integrated over the whole volume. The Boltzmann factor is just 1, so I just get the volume to the n minus 2. Now, this term, the first term, also simplifies. And so this integral, d3 R1, d3 R2, both over the volume of the system, delta of R minus R1 minus R2 times any function I claim that this thing is equal to V times F. Sorry, this is meant to be R12. I claim that this is equal to V times F of R. So why do I claim that? So if I make the change of variables, I've got an integral d3 R1 d3 R2. So I can make a change of variables in terms of R1 minus R2 and R1 plus R2 over 2. I'm not going to go through and do it. So then what's going to happen is, in terms of R1 minus R2, think of it like this. The system is translationally invariant. And the integral only depends on the difference between R1 minus R2. So I've got the integral d3 R1 d3 R2 times some function of R1 minus R2. So how can I do that integral? Well, just choose particle R1. Remember R1 and R2 are going over all points in the system, and the system is going to be large. So just fix particle R1, then R1 minus R2 will be any number, will be every distance that's possible in the system, which is going to be infinity. So keeping R1 fixed, and then integrating over R2 will give me some number. And then if I now average over R1, that will just give me a factor of V. So let me say that in a bit more succinct way. So if I take this integral here, then I claim that this integral does not depend on R1. So let me give you an example. Suppose I had the integral from minus infinity to infinity d dr2 e to the minus r1 minus r2 squared. Okay, so you tell me whatever R2 is, choose a number, 3, 16, 195, a million. Now I'm going to vary R2 from minus infinity to plus infinity. The answer I'm going to get is just going to be a number like root pi, and it's not going to depend on, R1. And then, now I integrate over R1. R1 can be in anywhere in the volume V, so then I'm going to get a factor of V on top of that. So therefore, this thing is equal to just the integral times the volume times that function. And what is that function? Well, the function is nice and easy, because in our particular case, the function that we're trying to integrate is this function here. And so where f of R12 is equal to, where this is e to minus u of R12 over kt. So what that means is, then what I end up with then is v times e to the minus u of r over kbt times v to the power n minus 2. So that's the numerator in g of r. And the denominator in g of r, well, now there's no delta function. To force particles 1 and 2 to be close together. So first approximation is that is just going to be, for each particle, it explores the volume, doesn't see any potential, and so you get v to the n, roughly speaking. So then what that means is, now I go ahead and divide. So so therefore, now plugging into my formula for g, I've got g of r is equal to v times v e to the minus u of r over kbt times v to the power n minus 2. And the denominator is, roughly speaking, v to the n. And so therefore I get that g of r is basically e to the minus beta times u of r. And that is definitely quick and dirty, but it's pretty much a really good approximation. So let's let's draw what that looks like. So this thing, wait. So this thing will look like this. So it will look something like that. Okay, so this value here, that value there is e to the epsilon naught over kt. This is r, and just to remind you, here's my potential. So there's the epsilon. I don't know why I called it epsilon naught. So there's what my potential looks like. So essentially, what you can see is that this behavior here, if there was no interaction potential at all, then this would be what I would get for an ideal gas. Then G was just a constant, independent of distance. So it just says of an ideal gas, the particles don't see each other. This normalized pair distribution function is just one. It's just a constant everywhere in space. There's no spatial dependence whatsoever. But this now does have spatial dependence, and this behavior here you can see in this range. There's what's called a correlation hole. And that's really very simple. If I've got two particles, they've got these hardcore repulsions, they can't get closer together than R naught. So therefore, the correlation function should basically pretty much go to zero when they are overlapping like that. So this correlation hole is basically the particle centers can't get closer than R naught because of the hardcore repulsion. So, and then what's going to happen if I've got two particles? Well, where are they going to be? Where the two particles are most likely to be, if they are correlated, they're most likely to be next to each other. So basically, so there's the particles, if they have some correlation, they're going to be sort of roughly close together. So this is going to have a higher probability when the distance is of order R naught, but slightly greater than, and so that's why you get this this peak at beyond R naught. So that's the reason for it. If I had a liquid, you could imagine that I've got my particles like this. So the particles are sort of sitting around each other at very high densities, and so you're going to have a high likelihood of having particles near this central particle. So there's going to be exclusion in here, and then there's going to be excess probability in this first shell around our test particle. And so this picture is what you see in liquids, for example, which have high density. So that's what this is what our expression gives us, and so that's that formula. So question.
So G of R is the correlation.
Pair distribution function, to be precise, yeah.
So, but for an ideal gas, since the particles are not interacting, why would the correlation not be zero? I mean, correlation is a measure of basically the potential, measure of the potential interaction between them, right?
No, it's a measure of the enhanced probability of being at a certain distance, depending on these interactions. So if the particles, if I've got a particle here and a particle here, and I say, what is the probability of having a particle here, particle here? It's not that the probability is zero. The probability is just a number which doesn't depend on distance. Okay, and then we've chosen the way we've normalized it is such that that number is equal to 1. Okay, does that answer your question? Yep. Okay, so now we've done the first thing. we've made an approximation to our 2-point correlation function. This is the first and easiest time you will ever see a correlation function computed in statistical physics or condensed matter physics or high energy physics. Yes.
Okay, I think I've been confused from the start.
Oh dear. Wait, how many lectures do I need to go back?
I don't think I completely, I understood the calculation afterwards, but I don't understand why you need the 3-point the 3-point function.
I didn't tell you that. I didn't explain it to you. I just told you, fun fact, if you try to, so here, I didn't use that.
Yes.
And you're saying, why didn't you use that? You said you had to use it, right? And remember, what I told you is that what we're doing here is this, a quick and dirty way.
Oh, so we just threw away like information relevant.
Yes, this is not correct. Okay, it's directionally correct, and it's an increasingly good approximation, low density, and you can justify it by a more formal thing, but it's not correct.
Could you explain again, it's also back further, I get why the terms where particles 1 and 2 are close dominate, so why do they have to be far away from the other particles?
Why do they what?
Why are they far away from like 3, 4, and
Because if they were near these other particles, then I have to take into account 3 body interactions. So I'm only taking into account 2 body interactions.
why does that, how do you know that dominates?
Because if they aren't close together, then the interval will just be the same length as numbers. If they're far apart, then the ultimate output will be really sweet as well. So we have a lot of value, we have to be close together.
Right.
So basically, so all I'm doing is I'm saying I can write down the integral, and then look at which terms are going to be the important terms. The only thing that's going to be not equal to 1 is that term. Did I answer your question? If they're if particles 1 and 2 are far
I
apart,
understand that.
okay, if they are closer to lots of other particles, then I have to take into account 3 body, 4 body, 5 body interactions, which I'm not going to do. And in any case, I've written down the potential as just the sum of 2 body interactions. So the first term that's non-trivial is just one where 2 particles are close together. Okay, one last question and I want to move on.
So, for when you graph the correlation function G of R, where it rises above just the constant,
Mhm.
constant is what is that a statement of?
It's a statement of what's on the right-hand panel, namely that the probability is always conserved. So the area in that correlation hole is equal to the area in the hump above the 1. And it just says that if there's particles that are close together, they can't get closer than their radius because of the hard core. So the closest they can get is going to be this like the ring that I've drawn here. And so there's going to be enhanced probability there.
So that hump, that's basically saying at that particular R, you're gonna have a higher probability of
Yes.
finding the curve
Yes,
space.
yes. Okay. All right. So this is great. So we calculated G of R, but we don't care about that. We want to what we actually want to calculate is the equation of state. So the next thing we're going to do now, let's go back to the equation of state. Okay, so what we're supposed to do, so remember what we derived was that PV over KBT is equal to 1 minus 2 pi n over 3 kBT, and then the integral from 0 to infinity of R cubed du by dr. du by dr, and then e to the minus u over kbt dr. So that's our formula. Okay, just remind you of the formula. So there's the formula on the left-hand side. Okay, so I left out a factor of n. PV over nkbt is equal to 1 minus that thing. And so our approximation for g of r is e to the minus u over kt. Then I've got du by dr, and then I've got the r cubed dr. So I have to do that integral. Okay. Okay, and this formula is absolutely not exact. We've made lots of approximations, most of them uncontrolled. So what we expect is that there's going to be corrections to this, and those corrections will be higher. The higher is the density of the particles, and so I'm going to write those corrections as order n squared. So we can imagine that this approximation that we've just derived, with a quick and dirty calculation, non-systematic, is nonetheless some sort of approximation that, if it's going to be valid anywhere, is going to be valid at low density. And so we get something like that. Okay, so that's the formula. So I want to now beat this formula down into a very nice form. Which we can generalize. So there's the result, and you can just do that integral, and then you're done. So the next thing we're going to do is next you might say, well, how can we generalize this? And make it precise and not hand waving it. So that's what we're going to do. So we're going to do that, and the answer is first of all, I'm going to show you a way to rewrite this. So I'm going to rewrite, and in doing that, I'm going to introduce to you a thing called the virial coefficient. So basically, in this lecture, virial is an adjective that applies to virtually everything. Okay, everything is virial. Okay, it's gone viral. So virial has gone viral. Okay, so well, I'm really loving my app at the moment. Okay, 189. Okay, so we're going to rewrite it to give you an idea of a thing called a virial coefficient, and then I'm going to show you how we can calculate these things systematically. So the goal now is to do some cosmetic rewriting in terms of something that we can systematically calculate. Okay, so here's my goal. So in the end, I'm going to propose that I can write down that P over KT is equal to N. So that's the ideal gas formula, right? So this term over here, this is the ideal gas. And then I'm going to tell you that we're going to write it down like this. We know the next term is going to be the term that comes from the corrections I've just calculated. So because I've multiplied through by n, see over here on the left-hand side, I've got PV over NKT. So that's where the n comes from. So the next term then is going to be something times n squared. And I'm going to call the coefficient in front of that, I'm going to call it B2. And B2 stands for second virial coefficient. And because this formula on the left-hand side has in it temperature over there, that temperature is in there because of our formula for the 2-point correlation function. So then this B2 is then going to depend on temperature. And then you might say, well, what's going to come next? So then there's going to be a term of order n cubed. And in fact, if I wrote down that term, it would be multiplied by a third virial coefficient, which I would write as B3. Okay, so let's write this down. So let's write down what our formula is. So our formula is that what we've just derived. If I look at our formula, I've got B2 of T is equal to the following. So I'm going to write it like this. So it's minus 2 pi over 3 kBt, the integral from naught to infinity r cubed du by dr e to the minus u over kBt dr. So that's a true statement. And now what I'm going to do is I'm going to do a very nice trick. I'm going to write this well, I've got a minus sign mistake here, so oh, no, I haven't. Nope, no, I haven't. I'm fine. So this is 2 pi over 3. And I'm going to get that factor of kt from my differentiation. So I'm going to write this then as naught to infinity r cubed, and then d by dr of e to the minus u over kBt. Okay? So think about that. If I differentiate that with respect to r, it's going to bring down a factor of du by dr. Then it's going to leave me a factor of e to the minus u over kt. And then I have dr. And what I'm going to do, the clever thing I'm going to do, is I'm going to put a minus 1 here. Okay? I'm going to put that minus 1 here, and then I have dr. Okay, so why did I put that minus 1 there? If I differentiate it, it gets 0, right? But you'll see where that comes from in a second. Okay, so there's nothing to stop me putting that in, so I've done it. So that's the clever bit. And then let's write this in the following way. Now let's do the integral. So I'm going to do the integral by parts. So this is going to be the integral from, so this is going to be r cubed times e to the minus u of r over kBt minus 1 between 0 and infinity, and then minus the integral from naught to infinity. So when you do integration by parts, what you do is you take the d by dr and it goes on to the other part of the integrand. So it's going to be the integral from naught to infinity, and then I'm going to have my factor e to the minus u of r over kBt minus 1. And then now I've got my d by dr acting on the r cubed, and so that's going to give me a factor of 3 r squared. So that's my integration by parts, and then close the bracket. Okay, so everybody follows that. Now, the limits on this, so when r is equal to 0, then the r cubed term is equal to 0, so that's 0. And when u is equal to infinity, then e to the minus u evaluated at r is infinity, well, the potential goes to 0. at r equals infinity. So e to the minus u over kt is then just going to be e to the minus 0, which is 1. And so I've got 1 minus 1, so that's going to equal 0 too. So this trick that we did has meant that this term over here, this term here is equal to 0 at both limits. And so then, well, now what I've got then is my B2 is equal to just this last term. And I'm going to write that last term as in the following way, as minus 1/2 the integral from 0 to infinity of I've got the 2 pi over 3, so this is minus 1/2 times 4 pi r squared dr times e to the minus beta u of r minus 1, like that. And then this thing here is just minus 1/2 the integral d3r of e to the minus beta u of r minus 1. So that's what our second virial coefficient is, now written down in this rather general and compact form. And this formula is we're going to generalize this. So I think this was first written down by Mayer. So this object here is going to be known as Mayer's f function. And so that is called, so this thing is equal to f of r is equal to e to the minus beta u minus 1. Okay, so that's our formula. Now let's have a look at what this thing means. So let's have a let's compute B2 of t from the Leonard-Jones 612 potential. And so let's have a look at what it looks like. So here is B2 of t. And what units does B2 have? What units does B2 have?
1/n, and the unit of n is
Volume, right. Because it's the integral d3r of exponential. So it has units of volume, length cubed. So we're going to normalize it by the only length that we have in the problem, which is our r star cubed. So we'll do it like that. And then I'm going to plot it here as a function of temperature, but the temperature comes in as kT, and then it's divided. kT has units of energy, so I'm going to divide it by the only energy scale in the problem, which is the binding energy epsilon. So then what happens is I get, so this is 0, 1, 2, 3, 4, 5, like that. And then the function looks something like this. Something like that. So that's what B2 looks like. Okay, so you can just calculate it. So this is kind of really interesting, right? Because look what happens here. So in here, B2 is negative. Here's this is -1, -2, something like that. So the way that B2 is coming in to the equation of state, so I've got P over KBT is equal to N plus N squared B2 of T plus higher orders. So what's happening is there's a temperature which is called TB, B for boil. There's a temperature TB where B2 of TB is equal to 0. And so for that one temperature, that means that P over KBT is equal to N, the ideal gas formula, plus a correction of order N cubed. And so that means that at that particular temperature, so this is the ideal gas formula. So at the boil temperature, the gas behaves more or less like an ideal gas. When B is negative, then the pressure is lower. When B is positive, the pressure is higher. So that's what happened. So here it's positive, here it's negative, and so for temperatures greater than TB, the gas is harder to compress. Than an ideal gas. And for T less than TB, it's easier to compress. And so that's that. And you might say, well, if it's easier to compress, well, can the whole pressure get negative? Well, in principle it could, but then you have higher order terms that would prevent that. And by the way, this happens here for gases. Similar things happen to polymer molecules in solutions. So if you do the statistical mechanics of polymers, there are analogs of this as well. Okay, so that's our quick tour of how you can do statistical mechanics, many body theory in a quick and dirty way and get reasonably good, interesting, physically meaningful results. So now I want to just give you an overview of how one does this in a formal way, in a systematic way. And I'm only going to give you the overview. I'm not going to expect you to master this. For one reason, I think there's computing quantitative corrections to gas equations of state and things like that is all very interesting. Computing Feynman diagrams in field theory and things like that, it's all very interesting. But what really matters is when all these expansions break down, when you get new phases of matter. So I'd rather spend more time on that than on very arcane and complicated calculations, which in the end just give you coefficients that aren't particularly interesting in and of their own right. They may have been interesting to know how to do it in practice during the 1930s when all of this was invented by people like Joe Mayer and so on, but it's not, if you need to learn it for your research, you should learn it and you should need to know it exists. If you're doing condensed matter, you'll need to know how to do Feynman diagrams and things like this. These are the same sort of techniques. So we're going to just go through now the formal theory of the virial expansion. And there's another expansion called the cluster expansion. So you should know that it exists, and it exists in all forms, all areas of physics. So it is the prototype of diagrammatic perturbation theory. For many body problems. In stat mech, solid state physics, field theory, even fluid mechanics. Okay, so this is sort of where you just sort of, you can, you know, I mean, hopefully you'll find it sort of vaguely interesting to know what people do. Some of you may find it really boring, and yeah, I can't disagree. It's not that interesting, but everybody should see it once in their life. So the goal is to say, well, I'm going to write down P over KBT. I'm going to write it down as an expansion like this. And I want a recipe that will enable me to calculate any virial coefficient that you give me. So if you say, hey, wouldn't it be great if we had the 112th virial coefficient? I'd say, yeah, sure, it'd be wonderful. Let's spend the next 6 years calculating it. Or we could just ask ChatGPT to do it for us, I suppose, or Mathematical or something. So all of these things can be automated. So let's do the basic idea. So of course, we're going to be using the configurational integral. So we're not going to use the virial equation of state, at least for this. We're going to just calculate the partition function exactly, and we don't need to compute the partition function with the momentum degrees of freedom, because we know that those are just Gaussian, and those just give you factors of the thermal de Broglie wavelength raised to the 3n power. So we've covered all that before. So all we need to do is the configurational integral, which is the integral over the volume of d3r1 to d3 Rn, at least for classical systems. I'm not going to deal with quantum systems. And then we have beta over 2, sum I not equal to j, u of r ij. So that's a thing that we want to compute. And so Mr. Mayer, Professor Mayer, I should say, said, well, let's define Fij to be e to the minus beta uij minus 1. So I'm going to call this this factor u of ij. I'm just going to call this uij. So u of rij is just uij, just to make it easier. So I'm going to define this function like this. And so and we've already seen that it has a nice property, namely that when R goes to I and J are infinitely separated, then this thing goes to 0, and when they're close, then it is some non-zero value. So it's basically a negative thing that goes to 0. So it basically looks so it basically looks like this. So when the particles are very close together, the potential is infinity. So what's going to be the value of the Mayer F function? It's going to be just -1, right? And then when the particles get very far apart, what's going to be the value of the f function? 0. So this is going to basically go something like this. And the scale here is going to be, roughly speaking, r star, something like that. That's the only scale in the problem. So this is a function which is nice because it's, if I want to do integrals with it, then it's easy to do. Okay, so that's what it looks like. So what's nice about it? Well, if I look at my Qn, I can write my configurational integral in the following way. It's the integral T3R1 up to T3Rn. And then I've got the product over I less than j, going from 1 to n, of 1 plus Fij. So it's equal to the product of those, because e to the minus beta u is 1 plus f. So this factor here this thing over here is equal to 1 plus f. And then because I've got the sum over u's, so then that is then the product. And so I get just something like that. So that's what the thing equals. So then we can just expand it. So then Qn is equal to the integral product over I equals 1 to n d3 ri, and then I have 1 plus, okay, so now multiply that thing out, okay? So there's going to be a term of Fij, then there's going to be a term which is Fij, Fkl, then there's going to be a term with 3 of them, and so on and so forth. So there's a huge number of terms, all coming from just multiplying 1 plus Fij. Okay, so you can think of this as 1 plus Fij, and then the product. So I over less than j. So there's one term, then there's an F12, then there's an F13, then there's an F14, and so on up to F1n. Then there's a term F. So I've got all of these things multiplied together. So then there's going to be terms F12, F23, and so on and so forth. Okay? So can you see that if I multiply that big product out, I'm going to get a whole bunch of terms like that. So it's just a huge mess. All right. So where do the diagrams come in? So what we're going to do is we write down each term as a diagram. So let me give you an example. Let's suppose that n was equal to 8. We had 8 particles in our system. So then what I would do is I'd write down particle 1, particle 2, particle 3, particle 4, particle 5, particle 6, particle 7, particle 8. So I'm just happen to write them down like that. And then I connect them with a line if they are if such a term exists in the integral. So let's suppose, for example, I have a line connecting that one and a line connecting that one. So then that thing can be turned into the following integral. That is the same thing as the integral from 1 to 8 d3ri, and then f34, f68. Okay, so then you might say, okay, let's do another one. So let's do this. 1, 2, 3, 4, 5, 6, 7, 8, like that. And so you might say, well, okay, how about this? We write down a line, say there's going to be a term like this, and a term like that. I can write down lines connecting any pairs of these vertices. So this thing would be the integral product from 1 to 8, d3 ri, and then f1, 2, f1, 4, f6, 7, and so I can do that. So we call these things n-particle graphs. Okay? So then we have a result. If you look at what Q is, then Q is just the sum of all distinct n-particle graphs. So that means that here's my job. If I want to compute the configurational integral, I have to first of all write down every single possible graph that is allowed by graph theory. And then I have to turn that into an integral and then do the integral. Okay, so that's the whole thing. So obviously if n is equal to 10 to the 23, there's a large number of terms here. And so the prospect of doing this for the rest of your life, in fact, until the end of the universe, is probably rather unappealing. So then the question we want to know is, are there simplifications? And the answer is definitely. So the answer is yes. So there's a whole slew of them, and some of them are obvious and some of them are not. So let's take a look at this last graph, the one that I have over here. Let's have a look at graph star, for example. So that graph factorizes. Because I can write it down like this. So it's equal to that. And then there's the graph 3, which is not connected to anything. There's the graph 5, which is not connected to anything. And then there's the graph 8, which is not connected to anything. And then there's the graph 6, which is connected to 7. So it factorizes into things like that. So these graphs are called connected graphs because they break if you take some scissors and cut one of the lines. Okay? So each graph is connected to at least one of the others in there. And if I have a connected graph with L particles in it, that's called an L cluster. Okay, so you could say, all right, well, write down all the 3 clusters. So you can write them down. There's one that looks like this. There's one that looks like this. There's one that looks like this. And then there's one that looks like this. So you can see that all of these things are dummy variables. So these three are the same. And the last one is not. So then you can say, well, okay, well, how much of this do I want to tell you? Well, I'll tell you this part, enough that you can understand the end result. So then there's a thing which I can do, where I can say BL, this thing is called a cluster integral. I'm going to define that to be 1 over L factorial thermal de Broglie wavelength to the power 3L minus 1 times volume times the sum of all possible L clusters. So you can define that, and if I were to take the ask what does it depend on, well, you can see that this is a function of the volume and the temperature. So you might say, well, we're interested in the thermodynamic limit. So V is going to infinity, N is going to infinity, the density is staying constant. So we're going to define another thing, which is BL with a slash is equal to, is a function only of T. And that is equal to the limit as V goes to infinity of BL, V, and T. So you can define that, and then you can go through and build all the n particle graphs from these L clusters. And so this ends up looking like this. When you do that, and I'm not going to go through the details, the configurational sum, which is what we're trying to do, is the following. So you can write it in terms of a quantity. I'm going to write it down and I'll tell you what it is. Okay, let me explain what these things are. And I'm not going to derive this or show you all the algebra that comes into it. So this thing here is, I take an n cluster and I say that it contains M1 clusters, M2 2 clusters, M3 3 clusters, etc. And then since the n particle, then n must be equal to the sum over L equals 1 to n L times ml. That's just because I have n particles in my graph, and I've got some graphs where I've got 1 particle, some graphs have 2 particles, some particles have 3, so the total number has to be n. So that's where this delta function comes from. And for any given value of n, of L, there are many different L clusters. And this quantity S is the sum of all n particle graphs constructed with M1 one clusters, M2 two clusters, and so on. So you have to work it out, and it's very unpleasant. But in the end, you get a very simple result. And I just want to end. So then you have to do lots of calculation. And they're in the notes. So I'm not going to go through them. And in the end, you get something that you can actually calculate. So in the end, you get something amazing. You get a formula for the grand partition function. So this formula is that the grand partition function of the system is equal to E to the power the volume over the thermal de Broglie wavelength cubed times the sum from L equals 1 to infinity of BL lambda to the L. And these B's are the things that I wrote down over here on the left-hand page. And this is the grand partition function. So this thing here is the fugacity. And why is this so amazing? Okay, so the first thing is, so the first thing you might ask is, wait, what? Why the grand partition function came in? Okay, can so you guys could actually guess the answer. So there's the previous page. Why did I introduce the grand partition function? So before we were computing in the canonical distribution, and we were just computing the configurational sum, the configurational integral. How did we suddenly end up with a grand partition function? So look at the left-hand page. Look at the formula for QA. Okay? You've seen something like that before. What's the hard part of doing? So never mind how you construct S. Okay, I skipped over all of that. It's in the notes. But what's the hard part about doing that calculation? Say it again, louder.
Constraints.
It's a constrained sum. It's a constrained sum. And what is our amazing trick for dealing with constrained sums? Go to the grand canonical distribution where everything factorizes. Okay, so look, we went to the grand canonical distribution because I'm talking about chi, and did everything factorize? Well, look, this is e to the something, e to the sum of a bunch of stuff. In other words, it factorized. Okay, So we got the fact, so the reason we use the grand canonical distribution, because this horrible many-body problem, using all of these graphs and everything, turns into a factorized thing. So y is a grand partition function to deal with the constrained sum. So that's the first thing. So that's that. And then next question. Wait, what? The BLs is only L clusters. And L clusters are what? Let's have a look on the previous page. L clusters are connected graphs. So BL is only connected graphs. But the actual thing the actual QN has disconnected graphs in it. Right? So like I've shown there in the middle of page 193. Okay, I've shown you how the thing factorizes. So it has connected graphs like the first and the last one, and a bunch of disconnected ones. Okay, but this whole formula has none of those. It only has connected graphs. Okay, so basically, what I've told you is yes, that's right. If you take E to the connected graphs, that equals to all the graphs. And it just comes from graph theory. It has nothing to do with evaluating the integrals. I haven't evaluated a single integral. All I've done is show you the topology of the graphs by drawing nodes and drawing lines between them. So this all comes from graph theory. Okay? And so in order to generate all the things that I need, there's a huge number of terms, and I can reduce it exponentially by doing this. So the graph theory enables us to reduce the huge amount of work, and this result, the one that is in the that is up there, this is called the linked cluster theorem. And this is a general result in many body theory due to graph theory. We still have to evaluate the integrals, okay? But at least now there's exponentially less to do. And now we have a basis for doing some kind of systematic, principled approximation method. Okay, so I'm going to stop there. There's still one more piece of this that needs to be done. There's another absolutely amazing simplification that comes out from graph theory. So I'm going to show you next time that as well. I'm just going to show you the end result. I'm not going to try to derive it for you. And then I'm going to show you what happens when you actually use these methods in practice to do real calculations for real materials. Okay. And when you've seen that, then you're going to understand why it is that I'm not proposing to spend 3 weeks just learning how to do these graph theory calculations and so on. Okay. All right. So I know this is like being deluged by a ton of oatmeal or porridge or something, but at least you've got some flavor for how one systematically goes about dealing with interacting systems. And every system of interest in physics, or even in other fields of science, they're all interacting. These techniques and things that come out of the physics that I'm going to be talking about, they are central to all of those things. Okay. And there's a reason why we never teach you any of this at undergraduate, because if you did, you'd never go to graduate school. Yeah. Well, if you want to do field theory, you want to do many body theory, and learn how to do these things. If you want to become a solid state theorist, well, then you may have to use these sorts of techniques. Although we've got even cooler ones these days. Okay, so that's it. So I'm going to stop the recording. Does anybody have any does anybody have any questions?